Coordination compounds looks difficult only until you see the pattern behind it. Hello students, welcome to the highest weightage chapter of 12th class, the theory of coordination compounds. First starting with types of salts. See, types of salts here mainly we consider first simple salt. How we define simple salt? Which contain only one type of cation, or you can say anion. Salts which can produce only one type of cation, anion, we refer it as simple salt. Like NaCl, it can produce Na plus, Cl minus, K2SO4, 2K plus, SO4 minus 2. Salts which can produce only one type of ion referred as simple salts. Coming to mixed salt, can produce more than one type of cation or anion. It may be cation or anion, but more than one type. Like CaOCl2 bleaching powder, Ca plus 2, Cl minus, OCl minus. So, two types of anions produced by CaOCl2, which is commonly known as bleaching powder. Then Na2HPO4, 2Na plus H plus PO4 minus 3, here two types of cations. Either it should produce more than one anion or more than one cation. Next, moving to another example, which we call it as microcosmic salt. Important JEE question. NaNH4HPO4 4H2O can produce Na plus, NH4 plus, H plus, PO4 minus 3. So here more than one cation, hence we can consider under mixed salt category. Next, moving to double salt. Double salt, mixture of two simple salts. First we need to mix two simple salts, dissolve it, melt it, dissolve it, then crystallize it. After crystallization, the resultant salt is double salt. Here you need to focus names as well as formulas. Potash alum, K2SO4, Al2SO4 thrice 24H2O, along with water of crystallization, you have to remember. More salt, FeSO4, NH4 twice SO4 6H2O, Carnallite, KCl MgCl2 6H2O, dolomite, CaCO3 MgCO3. Names as well as formulas you have to remember along with water of crystallization. Then coming to complex salt. Complex salt, or you can say coordination compounds. So complex salt are coordination compounds which can produce at least one complex ion. At the same time, the complex ions are those which cannot be dissociated further into simpler ions under normal conditions. So they exist in same format without dissociating further under normal conditions. One example you see here, complex salt K4FeCN6 which dissociates into 4K plus FeCN6 which is complex ion. This particular ion can exist like single entity under normal conditions, but under high temperature conditions further dissociation occurs. But normal conditions exist like simple ion. See some important terms required for coordination compounds. Coordination sphere. Coordination sphere, which is we show with a square bracket, coordination sphere, where inside coordination sphere central atom as well as ligand present. Coordination sphere meaning a square bracket inside which central atom, ligand enclosed. Central atom it is generally metal atoms which have vacant orbitals so that they can accept lone pair of electrons from ligands. We know electron acceptor is Lewis acid. So Lewis acid it is accept electrons. So central atom is, here it is Lewis acid. Ligand which can donate lone pair of electrons to central atom. It is the Lewis base. Why? The one which can donate electrons we consider it as Lewis base. So ligand. Classification of ligands. First classification here based on charge. Based on charge we are going to classify like positive, negative, neutral. Positive ligands like NO plus, negative ligands Cl minus, Cn minus, neutral NH3CO. Purely based on charge. Like NO plus is known as nitrosonium ion. So first classification based on charge. Second classification based on denticity. Based on denticity. Denticity meaning, first of all you see here, it is defined for ligands it is equal to number of coordinate bonds. Coordinate bonds are sigma bonds formed by ligands. So denticity is equal to number of coordinate bonds that can be formed by ligand. If it can form one bond, denticity is 1. It can form two bond, denticity is 2. So based on denticity, first monodentate ligand, where which can form one bond, so denticity is 1. Like all these examples, NH3, OH minus, Cl minus, all these examples here, Py is pyridine, Cn minus, NO2 minus, CO, carbon monoxide, NO, pyridine, F minus, H2O. So all this coming under even PPH3, triphenylphosphine. Important, triphenylphosphine, which is monodentate neutral ligand. Triphenylphosphine. All these ligands can form only one bond. Bidentate ligands, denticity should be 2. Denticity 2, so which can form two bonds. Such examples here given. See all these examples you have to remember. If you want to even note down, if you want to once again refer it, you can pause the video and refer it. Bidentate ligands, CO3 minus 2, C2O4 minus 2, oxalate ion it is. Ethylene diamine, which is important in this chapter, NH2, CH2, CH2, NH2. Here arrow marks whatever I showed, these are coordinate bonds. So nitrogen forming two coordinate bonds in ethylene diamine structure. It is ethylene diamine structure. Shortcut we write it as EN. Bidentate ligands. Next, another example for bidentate glycinate. We refer it as GLY, glycinate. NH2, NH2, CO minus. Structures you have to remember. Another bidentate dimethyl glyoxime, DMG. Example given, respect to structure you have to remember. Propylene diamine, we consider it as PN structure. Acetyl acetonate ion, in shortcut ACAC. All these shortcuts you have to remember because in exam they give in terms of shortcuts only. ACAC given formula. Tridentate ligands. Tridentate ligands here, denticity is 3. Diethylene triamine. One example, see here arrow marks I showed 1, 2, 3. All these 3 arrow marks are coordinate bonds. So this particular molecule can form 3 bonds with metal atom, central atom. Tetradentate denticity is 4. Like triethylene tetraamine. See triethylene where it is 1 CH2, here also CH2, 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 NH2, here NH2, NH2. Triethylene tetraamine. Why tetraamine? 1, 2, 3, 4. 4 NH2s. That's why tetraamine. Similarly, pentadentate ligands. Here see. This question asked in JEE. Pentadentate ligands. Ethylene diamine triacetate ion. Ethylene diamine triacetate ion. Like EDTA minus 3 you can mention. EDTA minus 3 meaning C. What is total negative charge? Here there is one negative charge, here there is negative charge, here there is negative charge. Overall 3 acetate ions, 2, 3, ethylene diamine, triacetate ion. Why triacetate ion? Because 3 acetate molecules available here. Minus 3 charge because overall molecule charge is minus 3. Blue color arrow marks whatever I showed, these are coordinate bonds which can be formed by ethylene diamine triacetate. Total how many coordinate bonds? 5. That's why denticity is 5 here. Pentadentate ligands. Next, tetraethylene pentaamine. Tetraethylene pentaamine. Another example, same like above. Here I wrote C. Triethylene tetraamine. So 3 ethylene molecules in chain followed by 4 amine molecules. That's why it is triethylene tetraamine. Here what we wrote? Tetraethylene pentaamine, 4 ethylene molecules and 5 amine molecules. Same like chain we have to extend it. Example under pentadentate ligands. Very important. Next, hexadentate ligand which can form 6 bonds. Example is EDTA or EDTA minus 4. Ethylene diamine tetraacetate ion. Minus 4 charge. Here hexadentate, minus 3 charge pentadentate. So where you can see difference. Here there is hydrogen but see here no hydrogen. Hydrogen is replaced by CH2CO minus. Otherwise, everything same. So how many bonds? 1, 2, 3, 4, 5, 6. 6 bonds it can form. That's why it is hexadentate ligand. See, observe it. Very important question. JEE question. Then you see one note here. Flexidentate ligand. Flexidentate meaning ligands for which denticity is not fixed. They can show more than one denticity. For example, sulfate can show denticity 1 as well as 2. EDTA can show 5 and 6. CO3 minus can show 1 and 2. NO3 minus can show 1 and 2. CH3CO minus can show 1 and 2. So different types of ions where denticity is not fixed. It changes from compound to compound based on availability of electrons or with respect to metal. Ambidentate ligands. Ligands which form bonds through two different donor atoms. Ligands which form bonds through two different donor atoms. Like for example, see, Cn minus can form bond through carbon as well as nitrogen. It can form bond through carbon as well as nitrogen. That's why two donor atoms. So Cn minus can form bond with metal atom through carbon as well as nitrogen. Similarly, CNO can form bond through oxygen as well as nitrogen. NCS can form bond through nitrogen as well as sulfur. Whatever hyphen I show, that is atom which is donating electrons or which is donor atom. ONO, NO2. So here oxygen is donor, here nitrogen is donor. Such type of ligands which can form bonds through two different donor atoms are ambidentate ligands. Normal ligands which can only donate electron pair to central atom and form coordinate bond. Normal ligands which can only donate electron pair to central atom and form coordinate bond. Regular normal ligand, like what is the role of ligand? Ligand can donate electrons to central atom and form coordinate bond, or you can say sigma bond. Such ligands, many examples we studied, few I am giving: NH2 minus, Cl minus, N minus 3, O minus 2, etc. Pi acid, pi acceptor ligands, important question here. Which can donate electron pair to metal ion? Which can donate electron pair to metal ion? But simultaneously, they accept electron pair from central ion through back bonding. So what's happening here? See now. Here there is metal, there is ligand. Ligand is giving electrons to metal, one sigma bond. In turn, back again metal is giving electrons to ligand. Due to increase in electron density on metal, which may lead to instability, first it is accepting electrons from ligand, then it is giving back to ligand. So a kind of back bond is formed. First bond is sigma, second bond is back bond. Pi acid, pi acceptor ligands. In simple terms, pi acceptor ligands are those which can form back bond with metal. Examples most important: CO, NO plus, Cn minus, R3P, R3As. Very important. Ligands which can form back bond are pi acceptor or pi acid ligands. One statement here: NH4 is not a ligand due to absence of lone pair of electrons. See, what is a ligand? Substance which can donate electrons to metal. But NH4 plus not having any lone pairs, which cannot donate any electrons, hence NH4 plus is not a ligand here. Okay. Once observe it, pi acceptor or pi acid ligands, very important question. Observe everyone, this one. Okay. Next continue. Next moving to chelation or chelation, anyway you can pronounce. Chelation here, what is chelation here? See phenomenon. It is made by polydentate ligands. Chelation, the phenomenon, or you can say phenomenon mainly observed in case of polydentate ligands. Polydentate ligands meaning denticity greater than 1. Denticity greater than 1. An extra chelate ring is formed. And an extra chelate ring is formed here during this chelation process. Chelation mainly observed in the ligands where denticity is more than 1. We call it as polydentate. An extra ring is formed. Which ring? Chelate ring is formed during such process. One example I am taking here, MEN. So what is EN here? EN is ethylene diamine. Remember, in this chapter, number of times we are going to repeat EN. For example, you see here there is metal M. Here there is one ethylene diamine molecule. Here also there is one ethylene diamine molecule. 2 EN we mentioned. So ethylene diamine, 2 amine groups. Ethylene diamine, 2 amine groups. Each molecule forming 2 coordinate bond because density is 2. Other side also it is forming 2. So now you see this part. How many membered ring it is? 1, 2, 3, 4, 5. It is 5 membered ring. Left side also you see with respect to M total again 5 membered ring. Chelation is the phenomenon where polydentate ligands form an extra ring, extra chelate ring with metal atom. During such chelation process, if 4 membered ring, if 5 membered ring or 6 membered rings are formed, those are more stable. See here 5 membered ring, here also 5 membered ring. Those are more stable. Whenever you get 5 membered, 6 membered, those are more stable compounds. Okay. Next, see further. Coordination number. Coordination number Cn, it is equal to number of sigma bonds or coordinate bonds around central atom. It is equal to number of sigma bonds or coordinate bonds around central atom. For example, see here. There is M, ligand, ligand, ligand. So here 3 ligands here, overall coordination number is 3. For example, you see NiCl4 minus 2. What is coordination number? Number of sigma bonds around central atom. Here there is chlorine. We know chlorine is Cl minus is monodentate whose density 1, which can form only one bond. It can form only one bond, right? So such monodentate ligands are 4 here. So 4 meaning here they form 4 bonds. Cl minus can form 4 bonds. Hence coordination number is 4. Here ethylene diamine is bidentate. We just now studied. Bidentate meaning it can form 2 bonds. It can form 2 bonds. How many such molecules? 3 molecules. Each can form 2 bonds. Such 3 molecules are there. Total 6 bonds formed. Hence for this coordination number is 6. Coordination number is 6. Next, MCl2En twice. Here it is monodentate and bidentate. Because chlorine is monodentate, En is bidentate. Coordination number 2 into 1. How 2 into 1? Because 2 chlorine atoms each can form 1 bond. 2 En molecules each can form 2 bonds. Overall coordination number is 6. See, I am explaining in sequence so that in less time if I cover entire theory part, so within less time we can cover entire like one shot theory part type. So if you have any doubts in between, you can pause the video and go through, so that you can cover the most of the chapter in less time. So next, MCl2En, just now we completed. NiDMG twice. So bidentate, so we know dimethyl glyoxime, bidentate. So 2, so 2 into 2, 4. Coordination number is 4. Next, see another term, oxidation number. Oxidation number, it is equal to charge developed on central atom if all ligands are removed. Simple terms, the charge on central atom. Overall it is. The charge on central atom is referred as oxidation number. We know already, in chemical bonding we studied. NiCl4, how we find? You take it as X, nickel take it as X. 4 into minus 4, total charge is equal to minus 2. X is equal to plus 2. We know carbon monoxide is neutral. So 5 into 0, X plus 5 into 0 is 0, iron is equal to 0. Cobalt, En thrice plus 3. Again, En is neutral molecule. So 3 into 0 we mentioned is equal to charge plus 3. Make it equal to plus 3. So here X is equal to plus 3. Oxidation number. Okay. Next. Iupac nomenclature of coordination compounds. Iupac nomenclature of coordination compounds. See, before entering into that, you see here, first K4 FeCN6. K4FeCN6. Whatever present in square bracket, we refer it as coordination sphere. Here metal is central atom and then Cn, which is ligand. Outside the coordination sphere, we consider outer sphere, whether left side or right side. Here, outside the coordination sphere, sometimes you may get cation or anion here, but outside the coordination sphere, we consider as Phi, outer sphere. Those are free ions. Okay. Rules you see now. Iupac nomenclature of organic compounds, coordination compounds. Rules you see now. Naming of central atom. Naming of central atom. See, when coordination sphere having 0 or positive charge, when coordination sphere having 0 or positive charge, then there is no modification in the metal name. Then there is no modification in the metal name. When? If coordination sphere having 0 or positive charge. Like for example, see, nickel CO4 compound given, here there is no charge. Nothing given means we take it as 0. If coordination sphere having 0 or positive charge, directly nickel we write as nickel, no modification. Here there is positive charge. See, positive charge. There is no modification, so we write it as chromium only. Rule number 1. Rule number 2. If coordination sphere having negative charge, then add suffix 8 to the metal. See, here coordination sphere having -2, here it is having -3. So -2, here it is nickelate, here it is chromate. Nickelate and chromate. Why 8 we added? Because coordination sphere having negative sign. Naming of ligands. Naming of ligands. So here naming of cationic ligands. Naming of cationic ligands. So here suffix is equal to IUM for cationic ligands every time. NO plus nitrosonium, NO2 plus nitronium, N2H5 hydrazinium, O2 plus dioxazinium. Okay. There you need to add IUM for cationic ligands. Neutral ligands, no modification of name. No modification of name. Benzene, H2O, aqua, anywhere, anything you can write. Pyridine. NH3, double M you have to remember. Amine it is, double M. Carbonyl for CO, nitrosyl for NO. PPH3, triphenyl. See, it is triphenyl and phosphine. This one phosphine. Dioxygen, octasulfur, tetraphosphorus, dimethyl ether, ethylene diamine. Neutral ligand. Ethylene diamine. Ethylene diamine. See now, ethylene diamine, EN. So these names you have to remember. Pause the video and write all these names. Next, anionic ligands. Anionic ligands, here name should end with O. See, for what we mentioned for naming of ligands. Cationic ligands, IUM you have to add. Neutral ligands, no modification. Anionic ligands, O you have to add, like chlorido or chloro, hydroxido, acetato, nitrato, nitrido, phosphido, azido, nitrito if it is N connected, nitrito O if O connected to the metal atom. Similarly, cyanate, OCN if O connected, cyanate to O. If N connected, cyanate to N. Why it is cyanate to N? Because here nitrogen connected. Here OCN, first atom is OCN connected to the metal. Similarly, thiocyanate, SCN minus, thiocyanate to S, NCS, thiocyanate to N. Why S and N? Because based on connection of S and N. Next, CN minus, cyanido C, NC minus, isocyanido, NC minus, isocyanido according to old system, or you can write cyanido N, Iupac system. Purely based on connection. If carbon connected, cyanido. If nitrogen connected, isocyanido. Next, NH2 minus, here it is amido. NH minus 2, it is imido. NH2 minus amido, NH minus 2, it is imido. And then CH3O minus methoxide. CH3O minus methoxide. Okay. Next, see here these examples you copy it. Then we moving to key points here. Some important key points you need to remember for writing Iupac names. Name of cation should be written first followed by anion. Every time cation first we write followed by anion. That is common, like sodium chloride. Sodium is cation, chlorine is anion. Number of free ions in outer sphere are not mentioned. See here free ions are potassium, right? Free ion. We should not write here tetra potassium. Number we should not mention. Only potassium we mention. So potassium correct. Free ions it is incorrect. Tetra potassium is incorrect. Name of ligand is written before central atom. See, first you have to mention central atom name. Sorry, ligand first we need to mention before central atom. Central atom last we will mention. So before that itself ligand's names you need to mention. Number of ligands represented by di for 2 di, 3 tri, 4 tetra, etc. If ligand is complex or if it contains di, tri, etc. in its name, complex substituents or you can say complex ligand, then we use 2 for bis, tris for 3, tetrakis for 4, pentakis for 5. Like how? Ethylene diamine, already there is di in its name. So that's why we use here bis ethylene diamine. Why? En twice. En twice, how we can write? Bis meaning here 2, remaining ethylene diamine automatically we write. Because it is, there is di, already di term in its name. If more than one ligand present, then follow alphabetical sequence. It is as usual, already you studied in 11th organic chemistry, same pattern. Di, tri, etc. are not included in the alphabetical sequence. We should not consider di, tri, tetra in alphabetical sequence. So these rules you keep in mind, key points. Now see the examples here. K4FeCN6, potassium hexacyanide 2. How? First of all, cation first we have to write, or for convenience you can write like this: 4K plus FeCN6 minus 4. Why minus 4? Here plus 4 charge, so you can minus 4 it will get. So how to start? First cation you have to write, number no need to mention, tetra potassium, so I wrote potassium for this one. Hexa for 6. Cyanide because it is negatively charged ligand. When we add O, if it is negative ligand, we have to add cyanide. See, coordination pair having negative charge. Whenever coordination pair having negative charge, what we write? 8 we need to write. So ferrate, what is oxidation number of iron here? This calculation done, 2 you got. X is equal to 2. Potassium, hexa, cyanide, ferrate because there is negative charge on a coordination pair, and then ferrate 2. The overall oxidation number is 2. Refer other examples, you will get much more clarity about it. See now. K3FeCN6. For convenience, I wrote 3K plus and then remaining complex. Iron is in plus 3 state. It is again negatively charged ligand. So potassium, potassium, hexa, hexa, cyanide, negative ligand, ferrate because there is negative charge. Charge it is 3. Which charge? Iron charge. So iron charge you mention in Roman number in bracket. Ferrate, that is 3. Okay. Observe both the names. Next. K3COC2O4. C2O4 is oxalate which is having charge minus 2. Cobalt is plus 3. Oxidation state, here C2O4 is minus 2 charge, negatively charged ligand. So potassium, yes potassium. Here what you will get? Here you will get negative charge only here. K3, right? So plus 3 means here minus 3 you will get. So potassium, tri, negative ligand, oxalato, cobaltate. Why cobaltate? Because overall here coordination pair you will get negative charge. That is how much? Minus 3 you will get. So cobaltate, the charge of metal plus 3, that is 3 in bracket in Roman numbers. Okay. See, next, another example, COH2O6Cl3, or for convenience you can write COH2O6 plus 3 plus 3Cl minus plus 3Cl minus. See here, plus 3 cobalt, H2O is neutral, H2O is neutral, so charge is plus 3. Hexa, yes, hexa, aqua, aqua, cobalt, here cobalt, 3 because charge is 3. Cobaltate we are not writing cobalt because coordination pair having positive charge. Whenever coordination pair having positive charge, we will not write any 8. So cobalt 3. Lastly, you can write chloride. See, first cation, it is cation, right? Then anion, anion, chloride. Clear? Next, K2PdCl4. Same, directly 2K plus another anion here. So now potassium, potassium, tetra, tetra, chlorido, chlorido, palladate, palladate, because it is anion, charge is minus, charge is 2. So you can write here charge as 2 here in this case. See, observe these compounds, everyone. Okay. Next, see methods to distinguish coordination compounds. See, Iupac nomenclature, like regular compounds we completed, and now after completion of this topic we will see even bridge compounds. Like whenever there is bridge ligand, means ligand which is connecting two metal complexes, such bridge ligands we are going to see after completion of this topic. We will see that. So methods to distinguish coordination compounds. Methods to distinguish coordination compounds. If two coordination compounds given, how to distinguish? See, reaction with AgNO3. Reaction with AgNO3. In outer sphere, if there is chlorine, whenever AgNO3 reacting, it forms white PPT of AgCl. In outer sphere, if there is bromine, if it is reacting with AgNO3, it forms AgBr, yellow PPT, pale yellow PPT. In outer sphere, there is iodine. If it is allowed to react with AgNO3, it forms AgI, dark yellow PPT. Dark yellow PPT. So when such two compounds given, one with 3 chlorine atoms, one with 2 chlorine atoms. So how to distinguish A and B? If it is allowed to react with excess AgNO3 here, easy. Whenever excess AgNO3 react, here 3 moles of AgCl is formed. How? Because 3 chlorine atoms available. 2 moles of AgCl formed because 2 chlorine atoms available. Based on number of moles of AgCl formed, one can identify whether compound having 3 chlorine in outer sphere or 2 chlorine in outer sphere. More number of AgCl moles, more number of chlorine in outer sphere. Less number of AgCl, less number of Cl atoms in outer sphere. So based on that you can distinguish A and B. Another method, reaction with BaCl2. Reaction with BaCl2, here sulfate, reaction with BaCl2, see, here it is reacting with sulfate BaCl2. So whenever there is sulfate in outer sphere, if it is reacting with BaCl2, it forms white PPT, BaSO4, white PPT. For example, see, I am taking compound A, there is SO4 in outer sphere, here white PPT is formed. Here there is no SO4 in outer sphere, so here no PPT of BaSO4 formed. Now you can distinguish A and B. The one which is forming white PPT of BaSO4 is A here, which is not forming is B because there is no sulfate in outer sphere. By using BaCl2 you can distinguish A and B. See here JEE question based on electrical conductivity. Remember electrical conductivity, number of ions directly proportional to electrical conductivity. Because more ions can carry maximum current. If number of ions same, then electrical conductivity directly proportional to charge on ions. Electrical conductivity directly proportional to charge on ions. Like see, how to distinguish by using these parameters, see now. I am taking compound A and compound B. Here there is Cl2 in outer sphere, Cl3 in outer sphere. If dissociation occurs, here it can form one ion and then 2Cl minus. Overall 3 ions you will get here. 2Cl minus 1 complex ion. Similarly, compound B can form 4 ions. How 4 ions? 3Cl minus 1, there is 1 complex ion. 3Cl minus 1 complex ion plus 3. Now, the electrical conductivity of B is greater than A. Why it is so? Because B can producing 4 ions, A producing only 3 ions. More ions it is producing, more is the electrical conductivity. It can carry maximum current. Okay. Then another compound you see, SO4 and Br. Both can produce 2 ions. Even here it can produce 2 ions. If same number of ions, you see here, if same number of ions, electrical conductivity depends on charge on ions. Where charge is higher, minus 2 plus 2 charge, minus 1 plus 1. Charge magnitude here it is more. That's why electrical conductivity of A is greater than B conductivity. Purely based on charge we are considering here. A greater than B, conductivity of A greater than B. Okay. Next, another method, reaction with H2SO4. We know H2SO4 is dehydrating agent. It is dehydrating agent. So whenever H2SO4 react with the compound where H2O present in outer sphere, there should be H2O in outer sphere. In such cases, if there is H2O in outer sphere, in such cases, dehydration occurs, so there is mass loss observed. Why? H2SO4 removes H2O. If H2O removed, automatically mass loss observed. Okay. For example, take compound A. Compound A, concentrate H2SO4. Here there is Cl3. There is no water in outer sphere. So that's why there is no mass loss here, as no H2O in outer sphere. As there is no H2O in outer sphere, so there is no mass loss. But in second compound, 2 H2O molecules available. 2 H2O molecules available. That's why mass loss observed in this case. But how much amount of mass loss observed? That we can calculate by using mass loss is equal to 2 into 18, because 2 water molecules, 18 is molar mass of water. X is total mass of compound into 100. Then automatically you get percentage mass loss based on number of water molecules. So these are the 4 methods by which one can distinguish coordination compounds. Whatever given coordination compounds you can distinguish. Okay. Next. Here you see now Iupac names of bridge compounds. See, regular compounds, normal compounds already we completed. Now, with respect to bridge compounds, how to identify? See now. Iupac names of bridge compounds. See, here I wrote A, B and then A. A here both are same. In between there is bridge. Symmetrical bridge. Why it is symmetrical bridge? Because on either side of bridge both are same. For such compounds, what you have to write? Name of A, name of bridge ligand, this one, plus name of A you have to write. Or micrometer symbol, that is new. New name of B, where you have to write new for bridge ligand. New name of B plus bis name of A. Plus bis name of A. Another category, unsymmetrical bridge. Unsymmetrical bridge meaning there is a B here. On either side, different groups are available. Same group symmetrical bridge, different groups unsymmetrical bridge. How we write here? Name of A, first this one you have to write. New name of B, this one. Name of C, this one. In sequence you have to write here A, B, C. Okay. Next you see. One example I gave here, see. Which type of compound it is? It is like, here it is A, here it is B, here it is A. Symmetrical bridge type compound. So what we named here? Pentaamine, because there are 5 amine groups. Chromium 3. And charges, how we need to assign? See here. Cl5, we know chlorine is -1, OH is -1. How many such chlorines? 5 chlorines, so overall charge is here -5. Here OH, so it -1. Overall charge is -6. So if minus 6 charge present in the compound, we need plus 6 to neutralize it. How we distribute? For chromium plus 3, another chromium plus 3. Plus 3 plus 3 distribute. Because common oxidation state of chromium is plus 3. You have to remember. Distribution done. So now pentaamine, here we mention chromium. Why it is chromium? Why not chromate? Because the charge of this given. For example, if you split it, what you will get here? 5Cl minus. So here plus 5 you will get charge. Plus 5 charge you will get, right? According to given sequence. So whenever coordination pair having plus 5, we will not write any chromate like that. So chromium, charge is 3. Yes, it is 3. New hydroxido. Why new hydroxido? Bridge ligand. New hydroxido. Then other side. So this part we completed now. Naming. Now think about this part. Again pentaamine chromium. Pentaamine chromium. 3 for chromium. Then lastly chloride. Or if you want to write new hydroxido. Other format. What is other format? You can write here ABA, other format what we showed. This one you see. New name of B, that is new hydroxido bis. Bis, instead of writing here again 2 times, just put bis and write pentaamine chromium 3 chloride once directly. That's enough. So here till here pentaamino chromium 3, then lastly chloride. Okay, keep here bracket and then chloride lastly. Okay, next see here double bridge given. Whenever double bridge given, again those two bridges you have to write in alphabetical sequence. First you see charge, how to identify. Sulfate, 2 sulfate ions present, so each is minus 2 we know. So total charge you see here minus 1, here minus 1. Total negative charge how much? Here 2 into minus 2 minus 4 plus, here minus 1 minus 1, so minus 6 available. How to distribute? Cobalt, chromium, 2 metal atoms. So remember chromium plus 3, cobalt plus 3. Common oxidation state of chromium, cobalt plus 3 plus 3. You need to remember whatever I am giving common oxidation states. After distribution, tetra aqua. Why we are writing tetra aqua cobalt? See same tetra aqua cobalt 3 amido hydroxido. Which comes first? Amido, new hydroxido, tetraamine. Again tetraamine, chromium 3, lastly sulfate. So bridge ligands if 2 follow according to alphabetical sequence. Okay, if any doubt, once again pause the video, refer once again those examples. Names of special compounds. Names of special compounds. Ferrocene. These are most important examples. Ferrocene, also known as bis cyclopentadienyl iron 2. Bis cyclopentadienyl iron 2. Like compound here like this. 2 cyclopentadienyl rings and then iron 2 in between. So iron 2 is in between, above and below 1 ring. 1 ring above, 1 ring below. Above and below. Okay. Next see here. Iron representation you see. Iron neta 5 C5H5 twice. Neta 5 C5H5 twice. Why C5H5? Ring it is represented as C5H5. Twice because 2. Neta 5. Neta meaning number of carbon atoms between which pi electrons are shared or present. Pi electrons are shared or present. See here now. These pi electrons shared between 5 carbon atoms or present between 5 carbon atoms. Okay, that's why here neta 5 we wrote. Why we are writing 5 here? Because pi electrons shared between 5 carbon atoms. Here also 5 carbon atoms. That's why we represented. Another example, Cr neta 6 C6H6 twice. Bis benzene chromium. Why bis benzene chromium? Bis because 2 benzene rings. Benzene, chromium, chromium. No charge for benzene. Why it is neta 6? Because the pi electrons inside pi electrons, it is present between 6 carbon atoms. That's why neta 6. Another compound, G salt. G salt, trichloroethylene platinate 2 ion, Iupac name. Representation C, PtCl3, neta2, C2H4 minus. It is ion. It is an ion. So PtCl3, how we wrote? PtCl3. And fourth bond is connected to C2H4. See, C2H4 given here. And overall charge is negative. That's why we wrote platinate. Whatever here I kept in box, this one is perpendicular to PtCl3. Not in same plane. It is perpendicular to PtCl3. Perpendicular to PtCl3. Observe it, everyone, PtCl3. Next, see here one important note, JEE question. Prussian blue. So Prussian blue, chemically known as ferric ferrocyanide. Prussian blue, that is dye color. Ferric ferrocyanide. So Fe4 FeCN6 thrice. Fe4 FeCN6 thrice. So ferric meaning here iron is in +3 state. Ferro meaning iron is in +2 state. That's why ferric ferrocyanide. Formula for Prussian blue, chemical name also remember. Another chemical substance, Turnbull's blue, which is exactly the opposite, ferrous ferricyanide. Here ferricyanide, ferrous ferricyanide. So Fe3 FeCN6, ferrous iron is +2, ferri iron is +3, and cyanide. AgCl, whatever AgCl precipitate form, it is soluble in NH3. It is soluble in NH3 due to formation of AgNH3 twice plus ion. AgCl formed, precipitate formed, soluble in NH3 due to formation of AgNH3 twice plus ion. Remember, chocolate brown PPT, main chemical formula Cu2FeCN6. Chocolate brown PPT, and AgNH3 twice plus ion responsible for solubility of AgCl in NH3. So AgCl soluble in NH3 due to formation of the compound, whatever soluble compound here. Okay, and close the note. Continue. Theory of coordination compounds. Theory of coordination compounds here, like first theory, basic theory, Werner's theory. Werner's theory, primary valency, secondary valency, introduced primary valency, secondary valency by Werner, which we call it as Werner's theory. So what is primary valency? See here. It is equal to oxidation number, primary valency, or you can say charge. Secondary valence is equal to coordination number. Coordination number meaning number of sigma bonds around metal. Number of sigma bonds around metal, we call it as secondary valency or coordination number. It is satisfied by negative ions, primary valency. Secondary valency is satisfied by negative and neutral ligands. Satisfied by negative and neutral ligands. Theoretical points you have to remember. Represented by dashed line, represented by solid line. It is non-directional in nature. Non-directional in nature meaning there is no particular direction to form. For example, ionic bond. Ionic bond is non-directional because ionic bond formed by force of attraction between ions, which is independent of direction. They can attract from any direction. It is directional in nature because secondary valency mainly by sigma bonds, you can say coordinate bonds or covalent bonds. Covalent bonds are directional in nature. They are formed by overlapping of orbitals only in particular direction. That's why it is directional in nature. Okay. Next you see Werner's representation of coordination compounds. Observe everyone, there is one compound CONH36Cl3. If they ask what is primary valency, that which is equal to oxidation number. Cobalt is in +3 state. Secondary valency is 6. Why it is 6? Because 6 bonds formed by 6 amine. Only ligands are those inside coordination sphere, not Cl. Inside coordination sphere you need to see. Representation how we show, secondary valence is 6. How? See 6 NH3. So all 6 NH3 you show with solid line, normal line. Primary valency 3. How primary valence is generated? Because of these 3 chlorine atoms. So 3 chlorine atoms you show by dotted lines. So it is, we call it as representation according to Werner's theory. Sometimes you will get a compound. See, Cl2 here negative charge. Here also there is one more chlorine. But this chlorine is inside bracket. So that's why we consider it as ligand also. So primary valency is 3. Why? Coordination oxidation number is 3. Secondary valence is 6. How it is 6? 5 bonds of ammonia, 1 bond of chlorine. So total 6. But representation you see how to show. Cobalt I showed here, cobalt. 5 amine, you show a solid 1, 2, 3, 4, 5. Inside there is chlorine, it is also ligand. So you show chlorine also with solid line. But the oxidation number, that is plus 3, is due to these 2 chlorine atoms as well another chlorine. Oxidation number is satisfied by these 2 chlorine atoms, another negative ion here. That's why for primary valency, we show one chlorine dotted line, another chlorine dotted line, second chlorine, whatever inside, third chlorine, whatever inside square bracket, one solid line already we showed, but it is acting as ligand as well as contributing towards oxidation charge, oxidation number. That's why for one chlorine we write both solid line as well as dotted line. For one chlorine, which is common for both ligand as well as oxidation charge, as oxidation state. You will get more clarity. See here now. CO plus 3, NH3, 4, Cl2. See now. Primary valency 3 because oxidation state is 3. How we got 3? Here minus 2, here minus 1. Total minus 3. So it should be plus 3. It is neutral. Secondary valency 6. How? 4 here, 2 here. 6. But how to show representation? See. Cobalt 5 NH3, 4. 1, 2, 3, 4. Fine. Next. 2 more chlorine atoms. Here 1 chlorine. Second chlorine we showed solid line. Come to primary valency. 1 chlorine outside, that is negative ion. So we showed here 1 chlorine. But these 2 chlorine also contributed towards oxidation number. Acting as ligand as well as contributing towards oxidation number. That's why these 2 chlorine atoms commonly we need to specify. Like here 1 dotted line, here also 1 more dotted line for this chlorine. So for 2 chlorine atoms which are present inside coordination sphere, 1 dotted line you have to show, 1 solid line you have to show. According to Werner's theory representation. Any doubt till here? Properly, if any doubt, properly refer once again video from starting onwards. So here many concepts we covered in this particular video about coordination compounds. Properly go through these theoretical concepts. In next video, we are going to continue from Sedgwick's effective atomic number rule, higher weightage topics like CFSC, crystal field theory. We are going to start in next video. First you complete the video, be ready for upcoming video. Thank you. Thank you very much.